Good morning, students. Palkana Namaskar. So, in the last class, we have discussed, we have started the chapter stationary view. In this chapter, we have discussed number of articles. In the last class, we have discussed free vibration, forced vibration, resonance, and end correction. Now, let us today discuss vibration of air column. Vibration of air column. What is air column? What do you mean by air column? Air enclosed inside the pipe. Air enclosed inside the pipe is called air column. Column is pillar. So we have two types of organ pipes. A pipe open at both the ends. A pipe open at both the ends is called open pipe. Open pipe. Another type of pipe, a pipe closed at one end. A pipe closed at one end is called closed pipe. Closed pipe. When stationary waves are sent, when the sound waves are sent inside the pipe, due to reflection phenomenon, stationary waves are found inside the two pipes, in open pipe as well as in closed pipe. The formation of stationary waves in closed pipe is different from the waves formed in the open pipe. How they are different, let us see one by one. So let us first discuss vibration of air column in a closed pipe. Vibration of air column in a closed pipe. Let us suppose what happens, let us see. What physics is taking place. Let us consider a vibrating tuning fork is held at the open end of the pipe. As we know that vibrating tuning fork means it is a sound waves. Sound waves consist of compression and reflections. First, and these sound waves travels through the air column and they reflect from the fixed end point. The reflected view and the incident view interfere each other. Stationary views are set up inside the air column. When vibrating tuning fork is held at the open end of the pipe, longitudinal wave propagates through the air column and these longitudinal wave reflect from the fixed end point. The reflected view and the incident view interfere each other. Stationary views are set up inside the air column. How the stationary views are set up depends upon the boundary condition. Let us see video is working or not. Okay. Let us suppose compression of longitudinal view. Let us suppose compression of longitudinal view is incident through the air column. When it reaches to the end point, fixed end point, as the particles of the closed pipe are not free to vibrate, as we can say that it is a denser medium. When longitudinal wave reflects from the denser medium, compression is reflected as compression. We have incident compression and reflected as compression. And when the reflected compression reaches to the end point, again it gets reflects. When it reflects from the rarer medium, as the particles of the medium at the open end of the pipe are free to vibrate as compared to particles inside the pipe. The density of particle inside the pipe is lesser than the here one. So what? Here the particles are free to vibrate, hence it is reflected as a reflection. And during this time, if the reflection of the wave reaches here, once again I repeat, initially compression is incident and this compression is reflected as compression. At the open end of pipe, it is again reflected as reflection. And during this time interval of time, reflection of that wave reaches at the open end of the point. They interfere each other and constructive interference takes place. Hence, always antinode is formed at the open end of the pipe, antinode, and at the closed end of the pipe, node is formed. Or we can in short say, due to boundary condition, as the particles of the medium at closed pipe are not free to vibrate, always node is formed at closed end as the particles of the medium at the open end of the pipe are free to vibrate, so antinode is formed. This is what the boundary condition, and the stationary waves are set up inside the air column in a pipe closed at one end. So, air inside the pipe or air column can vibrate in different ways. It can vibrate in different ways. The simplest way is air column can consist node and antinode. Simplest way. Or above from it may consist two antinodes and two nodes, three antinodes and three nodes. So air column, same length of air column can vibrate in different ways. The different ways of vibration of air column is called modes of vibration. Of air column. When stationary waves are set up inside the air column, it can vibrate in different ways, or it can vibrate in different ways, different frequencies may produce. The different ways of vibration of air column is called modes of vibration of air column. How the frequencies are produced, let us see one by one. That is modes of vibration of air column. So in order to study the modes of vibration of air column, let us draw the diagram. Least 3, minimum 3. Closed pipe, another pipe of same length, same diameter, figure A, figure B, figure C. Simplest mode. Node, antinode. Due to end correction, antinode forms a slightly above it. Length of air column, small l. So total length from antinode is capital L. In first mode, a antinode and a node is formed. A single antinode and a node is formed. That in this case frequency be n and wavelength be lambda. In second mode say antinode forms slightly above it, say antinode, node, antinode, node. Length of air column, small l. Total length from the antinode is capital L with addition of end correction. In third mode, say in this mode, B, n be the what? N1 be the frequency, lambda 1 be the wavelength. Small l be the length of air column which does not changes, remains constant. In this mode, say in third mode, first mode, second mode, third mode. Okay. Antinode is formed slightly above it. From this distance, capital L, node, 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 antinode, antinode, antinode. So, from this, for the same length of air column, we can observe that air column can vibrate in different ways with a different frequency and free wavelength. In this the frequency is n, wavelength is lambda. In this case frequency n1, wavelength lambda 1, and in this case frequency is m2, wavelength lambda 2. So in figure A, the air column can vibrate in simplest mode of vibration. If small l is the length of air column and L, that is corrected length, is small l plus E. What is E? E is end correction because a antinode does not form exactly at the open end of the pipe. In the simplest mode of vibration of air column, in figure A, one antinode node is formed. Antinode and node. One antinode and node is formed. Let n be the frequency, lambda be the wavelength of the wave. Then from figure, L is equal to, capital L is equal to distance between successive antinode and node is lambda by 4. Lambda by 4. Or lambda is equal to 4L. But V is equal to n lambda, or n is equal to V upon lambda, or n is equal to V upon lambda is 4L, or n is equal to V upon 4 small l plus e. So n is the frequency of vibration of air column in a simplest mode of vibration. This frequency is called fundamental frequency. N is called fundamental frequency, or it is called first harmonic. First harmonic. The next mode of vibration of air column is as shown in figure B. It is made to vibrate such that in between a node and antinode, antinode and node are formed at open end and close end. Apart from these two, other two node and other antinode and node is formed. Or in short, we can say that in this mode of vibration of air column, we see that two antinodes and two nodes are formed. So the character length of air column, in this case L is equal to, as we have seen that n1 lambda 1 be the frequency and wavelength of the wave. Distance between successive and node and antinode, distance between successive nodes is lambda by 2. Node and antinode is lambda by 4. Or lambda 1 by 2 plus lambda 1 by 4. Lambda 1 by 4. We get, or which is equal to 3 lambda 1 by 4. Or lambda 1 is equal to 4 L upon 3. We know that N1 is equal to V upon 4 L1. N1 is equal to V upon lambda 1 say. N1 is equal to V upon L1, or N1 is equal to V upon lambda 4L upon 3. 3 goes in numerator, or 3V upon 4L. 3V upon 4L. Or we can write N1 is equal to 3V upon 4 small l plus e. What is L? Small l is what? Length of air column. So if you compare this equation 1, or say this equation number 2 to equation number 1, we get that N1 is equal to 3N. Therefore, the frequency of vibration in this mode is called, N1 is called first overtone. N1 is called first overtone, or this is also called third harmonic. Third harmonic. If you compare N1 to N, we get N1 is equal to 3N. So frequency of vibration of air column in second mode is called first overtone or third harmonic. The next mode of vibration of air column is as shown in figure C. It consists of 3 antinodes, 1, 2, 3, and 3 nodes, 1, 2, 3. So in this case, let N2 be the frequency and lambda 2 be the wavelength of the wave. The corrected length of air column will be L is equal to lambda 2 by 2 plus lambda 2 by 2 plus lambda 2 by 4. Lambda 2 by 2 plus lambda 2 by 2 plus lambda 2 by 4. Half plus half is 1, 1 plus quarter is 5 by 4. Or L is equal to 5 by 4 lambda 2. Or lambda 2 is equal to 4 L upon 5. Similarly, N2 is equal to frequency of vibration in this case is V upon lambda 2, or N2 is equal to 5 goes in numerator, we get 5V upon 4L, or N2 is equal to 5V upon 4 small l plus E, or N2 is equal to what? We have arrived the equation 5V upon 4L plus E, or comparing N2 with this equation 1, we get N2 is equal to 5N. Hence the frequency of vibration in this case, in this mode of vibration, is called, N2 is called second overtone. Second overtone, or it is called fifth harmonic. If the frequency of vibration of air column in first mode is N, it is called fundamental frequency or first harmonic. Frequency of vibration in second mode of vibration is N1 is equal to 3 upon 4L plus T. We arrive at N1 is equal to 3M, which is called first order or third harmonic. Frequency of vibration in second mode is called first overtone or third harmonic. And we are arrived that in third mode, N2 is equal to 5V upon 4N plus E, or N2 will 5N, or frequency of vibration is said to be second overtone or fifth harmonic. From these three examples, or from these three observations, we can conclude that, what do we conclude? We can conclude that if M is the frequency of vibration of air column, if M is the frequency of vibration of air column, you close the pipe. If N is fundamental frequency, first overtone will be 3N, second overtone will be 5N, third overtone will be 7N dash 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 dash. First fundamental frequency, first harmonic, first overtone, third harmonic, second overtone, fifth harmonic, third overtone, seventh harmonic, so on. Or in general, we can say that frequency produced in a vibration of air column in a pipe closed at one end are odd multiples of fundamental frequency. Odd multiples of fundamental frequency. Frequency produced in the vibration of air column in a pipe closed at one end are odd multiples of fundamental frequency. Or frequency of vibration of air column in pth overtone, P is given by 2P plus 1 into N. What is N? N is the fundamental frequency. P is the overtone, where P is equal to 1, 2, 3, dash, 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 dash. If you substitute 1, first overtone, we get 3N. If you substitute 2, 5N. If you substitute 3, we get 7N. If you substitute 4, we get 9N. Like this. Or in short, we conclude that the frequency of vibration of air column in a pipe closed at one end are odd multiples of fundamental frequency, or odd harmonics are present as overtones in a vibration of air column. Next article is कितने सारे 27. So similarly, let us study vibration of air column in an open pipe. In an open pipe, that is a pipe open at both the ends. Let us see what happens in open pipe. What is open pipe? A pipe open at both the ends. A pipe open at both the ends is called open pipe. Let us suppose when a vibrating tuning fork is held at the open end of the pipe, longitudinal waves travels through the air column, that is air enclosed inside the pipe, and these longitudinal waves, when they arrive at the open end of the pipe, they get reflected. Why do they get reflected? Because when the air is enclosed inside the pipe, in middle of the pipe, density of air is equal to mass upon volume. Volume is small here, so density is larger. In middle of the pipe, the density of air is large. When at the outside the pipe, the volume of air is larger, so density is small. Or we can say that it is denser medium, it is a rarer medium. The density medium, it is a rarer medium. And due to the rarer medium, due to boundary condition, the incident wave partially reflected, not totally. In closed pipe, wave reflects totally. In closed pipe, incident wave reflects totally, but in this case, the incident wave is reflected partially. And when it reflected partially, again when it arrives at the open end, again it reflects. Incident wave and reflected wave interfere each other. Stationary waves are set up in the string. Stationary waves are set up in the air column. Provided the condition is that, let us say, the compression of longitudinal waves passes through the air column. When it appears, when it reaches to the open end, due to rarer medium, it reflects as rarefaction. Compression is reflected as rarefaction. Again, this rarefaction reaches to the opposite end of the pipe, it is reflected as compression. And during this time interval, the compression of second wave reaches here, not the first wave. Compression of second wave. Compression of first wave incidentally, it has been passed to the air column. So compression of second wave appears here and constructive interference takes place. Stationary waves are set up inside the air column such that always antinode is formed at open end and node is formed in between. These were the boundary conditions. According to boundary condition, when a stationary waves are set up inside the air column open at open pipe, boundary condition suggests that always antinode is formed at open end and node is formed in between. So air column can vibrate in different ways. The different ways of vibration of air column is called modes of vibration of air column. Modes of vibration of air column. Let us study modes of vibration of air column in a pipe open at both the ends. Open at both ends. So let us draw again diagram. Let us draw three pipes of equal length. Equal size. Of equal size. Let L be the length of air column. Now, according to boundary condition, minimum antinode is formed, always antinode is formed at open ends. So from this point, the corrected length will be L. So let us draw the diagram. Node. Dotted line shows reflected waves and thick line indicates incident wave. This was the first mode of vibration. In this case, let's say n be the frequency, lambda be the wavelength of the wave. In second mode, same length. Length of air column small l. Antinode is formed slightly above. Antinode is formed slightly above. Length of air column. Length, corrected length capital L. Antinode, antinode. So what? Let us take 2 points. Antinode, node, antinode, node, antinode. Okay, next, last case. Let L small l with the length of air column. Again, antinode is formed at open end at the same level. Antinode is formed at the same level. Okay. Corrected length L, capital L, as shown in figure. Antinode, node, 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 antinode, antinode. Figure A, figure B, figure C. So you can observe from the diagram, air column can vibrate in different ways. The different ways of vibration is called modes of vibration of air column in a pipe open end, both the end. In first mode of vibration of air column, it consists of what? 2 antinodes and 1 node. It is made to vibrate such a way that node is formed in between 2 antinodes formed at open end. So this is what simplest mode of vibration of a air column. Let m be the frequency of vibration, lambda be the wavelength. Then corrected length L is equal to distance between node and antinode is lambda by 4. As the wavelength is lambda. Lambda by 4 plus lambda by 4 is lambda by 2. Lambda by 2. Or lambda is equal to 2L. But V is equal to N lambda. Or N is equal to V upon lambda. Or N is equal to V upon 2L. Or N is equal to, as correction is applied in both the sides. End correction, this distance is E small e. This distance is small e. It is applied in two sides. Therefore, N is equal to V upon 2L plus 2E. The frequency of vibration In the first mode is called fundamental frequency. Fundamental frequency, or it is called first harmonic. The next mode of vibration is as shown in the figure B. Always antinode is found at open end. Two nodes and single antinode is found in between, as shown in figure B. Let in this case N1 be the wavelength, the frequency, and lambda be the wavelength of the wave. Then the length of air column L, capital L, is equal to lambda 1 by 2, lambda 1 by 2, lambda 1 by 4 plus lambda 1 by 4. Lambda 1 by 2 plus lambda 1 by 4 plus lambda 1 by 4. Quarter plus quarter is half, half plus half is 1, or L is equal to lambda 1, or N is equal to, in this case, N1 is equal to V upon what? Lambda 1, or N1 is equal to V upon lambda 1 is how much? L, or N1 is equal to V upon L. What L means? Capital L plus 2E, small l plus 2E. If you compare N1 with L, we get N1 is equal to 2N. Hence, the frequency of vibration in this mode is called first overtone, or it is called second harmonic. Second harmonic. Frequency of vibration in this mode is called, as since N1 is twice of N, and it is next higher than the fundamental frequency, it is called first overtone. As it is multiple of 2, it is called second harmonic. The next mode of vibration is shown in the figure C. It consists of 1, 2, 3, 3 antinodes and 3, 1, 2, 3. So these are 4 antinodes and 3 nodes. Let in this case N2 with the frequency and lambda 2 with the wavelength, then capital L, length of vibrating length or air column is lambda 2 by 2 plus lambda 2 by 2, lambda 2 by 4, lambda 2 by 4. Lambda 2 by 2. Lambda 2 by 2, lambda 2 by 2 plus lambda 2 by 4 plus lambda 2 by 4. Quarter plus quarter is half, half plus half is 1, 1 plus half is 3 by 2. 3 by 2 lambda 2, or lambda 2 is equal to 2L upon 3. Similarly, N2 is equal to V upon lambda 2, or we get N2 is equal to lambda 2 is 2L by 3, 3 will goes in numerator, 3V upon 2L, or N2 we can write as 3V upon 2L small l plus 2E. Why 2E? End correction is applied in both the sides. Or N2 is equal to, we can write it as, if you compare with this fundamental frequency, we get N2 is equal to 3N. Hence, it is the next frequency greater than first overtone. It is next higher frequency than the first overtone. It is called second overtone. N2 is next higher frequency than the first overtone. Therefore, it is called second overtone. And as it is multiple of fundamental frequency, how it is multiplied? 3 times. Therefore, it is called third harmonic. Third harmonic. Once again I repeat. In simplest mode of vibration, only 2 antinodes and node is formed. If we derive the expression for frequency, we get n is equal to upon 2L plus E. Frequency of vibration is called fundamental frequency, or it is called first harmonic. In second mode of vibration, 3 antinodes and 2 nodes are formed. If we derive the expression for frequency of vibration, we arrive that N1 is equal to V upon L plus 2E, or N1 is equal to 2N, which is higher than the fundamental frequency. It is called first overtone, or it is called second harmonic is multiplied by 2. Similarly, in third mode of vibration, as shown in figure C, 4 antinodes and 3 nodes are formed. If we derive the expression for frequency, we arrive that N2 is 3V upon 2L plus 2E, or N2 is equal to 3N. The frequency of vibration in this case is called second overtone because it is higher than the first overtone. As we multiply by 3, the fundamental frequency, or it is called third harmonic. Or, in short, we can write frequency produced in a vibration of air column in a pipe open at both the ends. If n is the fundamental frequency, first overtone is 2n, first overtone is 2n, second overtone is 3n, similarly 5n, 6n, 7n. Or we can state like this way. Overtones produced, overtones are 2n, 3n, 5, 3n, 4n, 5n, 6n, 7n, dash. Or overtone produced in a vibration of air column in open pipe are integral multiple of fundamental frequency. Integral. Fundamental frequency, integral multiple. n, 2n, 3n, 4n, 5n, 6n, 7n, 10. Overtones are integral multiple of fundamental frequency. Or in other words, all harmonics are present as overtone. All harmonics are present as overtone. Or frequency of pth overtone, in this case Np is equal to N into P, where P is equal to what? 1, 2, 3, dash. N is fundamental frequency, or PNC, we can write P into N. Or in short, we can say that in closed pipe, some frequencies are blocked. Closed, they are blocked. Which frequencies are blocked? Even frequencies are blocked. And in open pipe, it is totally open. That is, odd and even frequencies are present, and they are integral multiple of fundamental frequencies. Okay, we'll stop here. Let us continue tomorrow. Bye.